In the last video, we took a look at what happens when you take air resistance into account in ballistic trajectories, and we also spent some time introducing the Rtz Coordinate System, which will be helpful at this point here. So let's go ahead and take a look at uniform circular motion. So let's say we've got an object that is moving around in a circle like so. If it's uniform circular motion, its velocity will be tangential to the to the circle. And since its speed isn't changing, there will only be a centripetal component to the acceleration. So it'll be directed towards the center of the circle, like so. So in this case here, in the Rtz coordinate system, we can break down our coordinates by saying that the radial component of the velocity would be 0. The tangential component would be the r omega that we saw earlier, and there is no z component. And by the same token, we can write that the radial acceleration, as we saw before, is v squared over r, or we could write that as r omega squared. There is no tangential component, and the z component is 0. And remember, for these omegas here, we have to be working with radians. So omega here would be in radians per second, for instance. All right, so with that as background, let's work through a few sample problems. So the first one I can think of is, let's say you're looking down at the surface of a table and you've put a nail into the center of the table. Please don't do that with the table you actually care about. And we've tied a little 10-gram mass on the end of a string. And we have it spinning around at a radius of 10 centimeters. Now let's say the string breaks if at a 50 Newton load. With that, I'd like to know what's the fastest speed for our washer, or sorry, for our little mass here. Well, we can go ahead and look at this point right here. We can throw up a quick Rtz coordinate system. So this would be the plus r direction, that would be the plus t direction, like so. And we can go ahead and write down Newton's second law in the r direction. So we would have that the net force would be equal to m times a sub r. Well, the only thing providing a force would be the tension in the string pointing into the center here. And we saw that the radial component of the acceleration would be v squared over r. So the speed at any time would be equal to the square root of tr over m. Now for our maximum speed, that tension would be 50 newtons. We would be timesing that by 0.1 meters over our mass of 0.01 kilograms. And that will give us a speed of 22.4 meters per second. So that's the fastest we could have this mass spinning around before our 50 Newton test string would break. So in this example here, where we're looking down on top of a horizontal tabletop, I'd like to ask just an additional question. What would happen to the motion of the mass if the string were to then suddenly break. Pause the video and get back with me. Yeah, it would go in a straight line because Newton's first law tells us that things want to go in straight lines at constant speed unless there's a net force. There are two additional forces, by the way. There is gravity and the normal force, but they're both in the z direction and they cancel each other out. So inertia would take over and it would travel in a straight line at a constant speed, tangent to where the curve, wherever it was, the string broke. All right, let's look at another example. This one is a classic known as a conical pendulum. Why it gets called a pendulum even though it doesn't swing back and forth is a little tricky, but the idea basically is that you just have a mass on a string and it's attached to some support up above, and you just let it go around in a circle in the horizontal plane. So I'm just going to draw off a plane here, label it, this is the horizontal plane. So if you're familiar with a tether ball, this would be an example of a tether ball here. The reason it gets called this, by the way, is you can show, I'm not going to show it here, but you can show that the time it takes for this to make a lap is the same time it would take for a pendulum of the same length to swing back and forth. Thus the name conical pendulum, even though it isn't really a pendulum. All right, so let's say this thing is going in a circle with radius 1 meter. Let's say it's going at a speed of 5 meters per second. What I want to know is what angle is our string hanging with respect to the vertical. Okay, so again, we can play the same kind of game here. We can set up an Rtz coordinate system. So this would be the t-axis, that would be the plus r axis, and then perpendicular. Yeah, I should have drawn the t-axis a little better. There we go. This is the t-axis. That's the r-axis. And then perpendicular to them both is the z-axis. And so if we draw a free body diagram of our mass here, we'll see that we have two forces. We've got, so this is in the RZ plane. We'll have the force of due to tension like that, and we'll have the force of gravity like that. And by alternate interior angles, this angle is also our angle theta that we would like to find. We can break our tension into components. This would be the R component of the tension, and this right here would be the Z component of the tension. So we can go ahead and write Newton's second law in the R direction. What we would have is the R component of the tension is equal to m times the R component of the acceleration. Well, so that's going to be t times the sine of theta. That'll equal m times v squared over r. Then in the z component, what we have is the z component up, and then gravity down will equal m a sub z. Well, a sub z we said was 0. And t sub z is going to be t cosine theta. So that'll equal fg, or we can write that t cosine theta is equal to mg. Now, we don't know what the tension is, nor were we asked to find it. In fact, I didn't provide the mass either, and that's okay. It'll turn out the mass cancels. So a fascinating thing here is that this is true regardless of how massive our pendulum, our object is that's attached to the string. So one way that we can, there are many ways that we can eliminate the t's between these equations. Certainly you could solve one of these for t and stick it into the other. But let me just show you another trick. This is called dividing equations, which you may or may not have seen before. So I can take something that's true, like my r equation, mv squared over r. Now, I can divide the left-hand side by the t cosine theta here, as long as I divide the right-hand side by t cosine theta. But here I'll choose to divide to write it as what's on the right-hand side, mg. So basically I've taken this equation and written it over this equation. So I've divided the left-hand sides of these equations and the right-hand side of these equations. So what we see happen is the m's cancel as advertised and the t's cancel. And we can clean this up a little bit. We know that sine over cosine is tangent. So the tangent of theta will be, if I go ahead and do this division a little further, v squared over rg. So the angle will be the arctangent, so it's just taking the arctangent of both sides, the arctangent of v squared over rg. So we can put in the numbers that we have for this. So this will be the arctangent of 5 meters per second squared over 1 meter times 9.8 newtons per kilogram. I promise you the units do all work out, and when you grind it through, you get an angle of 68.6 degrees. All right. So we've also seen that earlier when we were mentioning weightlessness and objects that are in orbit, we said that those objects were falling around the planet or the star or whatever. So say this is my planet, an object that's going in a circular orbit around it, like so. The idea is that you have to be going sideways so fast that, here, let me make it go the other way. You have to be going sideways so fast that as it's constantly falling to the center of the Earth, it keeps curving around and missing. So in other words, we end up going into uniform circular motion. There. So here, remembering that g is not an acceleration, and at this altitude, g is almost certainly not equal to 9.8 newtons per kilogram here. It's just equal to whatever it is equal to. This for the altitude of the International Space Station would be 8.9, for instance. It's true that you can always write that the force of gravity is mg, as long as we acknowledge that g doesn't have to be 9.8. It can be whatever. So then we can do the same game as we've done before. We can say that in this case, gravity is the only force I have acting in the radial direction. It has to be equal to m times a sub r, or mg equals mv squared over r. So I can go ahead and cancel the m's. And what I get is that the speed of my satellite is equal to v is equal to the square root of rg. We'll call this the critical speed, because it'll show up in a couple of other guys as we go along. But for now, this is the speed that you will be going if you are in a circular orbit around a planet. Again, recognizing that g varies with distance. From the center of the planet. All right. So one application of this is Kepler's third law. Also known as his harmonic law. If you remember Kepler's laws of planetary motion, the first law was that a planet orbits the sun in an ellipse with the sun at one focus and the other focus vacant. Kepler's second law says that is the equal areas for equal times thing. Then the third law said that the square of the orbital period goes as the cube of the orbital radius. So let's go ahead and take a look at that one there. So let's say we've got the sun here. Mass big M. And I'm just going to draw a chunk of some planet's orbit here, mass little m. So we'll pretend that the orbit is circular, and this turns out to be not a bad approximation for every planet except Mercury basically, and Mars. For all the others, yeah, like the Earth's orbit is an ellipse, but if you were to print the ellipse out on a piece of paper without drawing in coordinate axes, you would swear it's a circle. Now, it's only if you put in the coordinate axes that you see that looks like an off-center circle. To your eye, it still won't even really look like an ellipse. So most of the planets have circular enough orbits that you can well and truly approximate them as circles. However, you can do this derivation correctly for elliptical orbits, and you get the exact same answer if you replace the radius of the orbit with the what's called the semi-major axis of the ellipse. However, the analysis is much more complicated. All right. Anyway, we've only got one force acting, and it is gravity. And we'll say that the orbital period of our planet is capital T. All right. So again, we can go ahead and say that gravity is our only centripetal force here. So this is going to be mv squared over r. Okay. Now for this, we're going to need Newton's law of universal gravitation here. So F sub g we'll write as g big M little m over r squared. And this will equal m. Now the velocity, since we're going in a circle, we can write the velocity as the distance traveled in one orbit, 2 pi r, the circumference of a circle, over the time it takes to do it, the period, big T squared, over r. Okay. So what we will end up with here is, well, we can cancel the little m's there, so it doesn't matter what the mass of the planet is. And by the way, this is sweeping under a rug, and the issue that we're basically pretending that the sun is stuck right in the center of the orbit. When you start extending this to things like moons orbiting planets, a more careful treatment will give you almost the same answer, but I'll tell you how to modify it if you need to. Anyway, so we get gm over r squared. If I take this and expand it through, this is going to give me 4 pi squared r squared over rt squared. I can lose 1 power there. And if I rearrange, I get that t squared equals 4 pi squared over gm r cubed. Now, if the thing you're orbiting isn't super duper massive compared to the thing doing the orbiting, a more careful analysis will give you the sum of the masses here. And actually that's just true in general, but say if you're looking at, you know, the Earth going around the sun, adding the mass of the Earth to the sun is no big deal. It's like the difference between weighing a dog with or without its fleas. But this is how we weigh a planet. So for instance, a way that you can weigh Saturn, so there's Saturn, is we can look at its moon Titan. It has careful astronomical observation shows that the orbit is basically nearly circular with a radius of 1,211,850 kilometers. And the orbital period of Titan around Saturn is 15.945 days. So what we can do is we can take Kepler's harmonic law and rearrange it. We'll get that the mass of Saturn, the thing you're orbiting, is 4 pi squared over gt squared r cubed. So this will be 4 pi squared over 6.67 times 10 to the negative 11 Newton meters squared per kilogram squared. Our period is 15.945 days, but we'll have to turn the days into seconds. There's 86,400 seconds in a day, and we will be squaring that. And then for our r cubed, the kilometers has to go into meters, so that's 1,211,850,000 meters. They don't call them astronomical numbers for nothing. And that's a cubed there. All right, if you punch this all through, looking at this, you'll get 5.55 times 10 to the 26 kilograms. Or if you prefer, that's 555,000 yoctograms, which is basically the first and last time you'll ever hear me mention that ridiculous prefix. But at least I guess it's useful when you're looking at planet-sized objects. So, yay, 500,000 yoctograms roughly. By the way, because of the squareds and the cubes and stuff like this, this number depends a lot on just how precise and how fussy you are with the calculations. And so I will say that the accepted value using more precise inputs is actually 5.68 times 10 to the 26 kilograms. But that is how any planetary object gets weighed. You go ahead and you look at something orbiting it. You measure its orbital period. For objects that don't have anything orbiting it, you wait for something like a comet to fly by it, and you take a look at how it gets deflected, and you can do a similar sort of calculation there to figure out the mass of the planet. All right. So I will finish up this video with a bit of a challenge question. If you look at an auto race happening, a technique that you'll see drivers do is something called cutting the apex. So say here's their race car there. Let's say it ends up over there. the racing line that they'll usually take will swing from the outside of the curve to the inside of the curve, back to the outside of the curve, like so. So my question to you is, why did they do that? Seemingly staying on the inside of the curve the whole time would be the shortest way around. Now, obviously, a race car driver is doing this because it'll give them a faster lap time despite driving a longer distance. But I want you to figure out why that is. Pause the video and get back with me. All right, so here's the deal. The deal is that by cutting the apex, the race car driver is going through a bigger radiused circle than any of the radii that the track is built around. So here would be the inside radius of the track. There would be the outside radius of the track. The force that is making the car go around the curve is static friction. And if a driver is at the limit of adhesion, that's going to be Fs max. And that will equal mv squared over r. Now, there's not much the driver can do about changing Fs max here, because this is mu static times the normal force. Now, if you look, so if we go ahead and draw a free body diagram here, so this is the z direction and this is the r direction. Free body diagram for the car is going to look like this, where you have the force of static friction pointing in, you've got the force of gravity down on the car, you have what's called the down force, which is actually a lift force. The wings on the back of a race car are actually bolted upside down compared to an airplane wing. So where it'll help an airplane wing fly up, this is done to push the car down into the ground. And by doing that, you force the normal force to be greater than the force of gravity. But even with all that, the normal force basically isn't going to change. So the idea here is that if this radius is bigger, that allows v squared to be bigger in proportion, since we're at the limits of adhesion here. And it turns out that this carrying this extra speed through the corner more than makes up for the extra distance traveled, and so that gives the driver a faster lap time. It'll also turn out that this downforce generated also depends on the speed of the car. So by doing this, you can actually generate a little more downforce and get sort of a beneficial feedback there. Alrighty. So in the next set of videos, we will continue along this looking at motions in a vertical plane, non-uniform circular motion, and then finally finish up with a little bit of a rant about fictitious forces. So we'll see you over there.